Good afternoon. My name is Cheng. I'm now a senior student in statistics at North Carolina State University. This semester, I'm doing a research project with my supervisor, Dr. Charles Smith. The project is about Gompertzian growth curves and rat tumors. And what we do basically is to estimate the parameter and model the tumor size by differential equations. Our project is concerned with parameter estimation for growth curves in implanted tumors in rats. The Gompertz curve, which will be introduced later, is used as the model with three parameters: R, the growth rate, K, the saturation parameter, and the variance parameter. The datasets are from the classical paper of Simpson, Heron, and Lloyd, and the data consists of measurements every 7 days up to day 77 on two groups of rats, one with the initial size 63 milligrams and the other 108. So the picture here shows a general Gompertzian growth for the number of cells versus time. It starts like an exponential growth and gets slowed down as the tumor size approaching to the saturation level. The line plot here of 108 milligram dataset with the axis of tumor size versus time. And the lines are grouped by different rats. As you can see here, there are a lot of variabilities among the curves. Here we have two dot plots for both datasets, still tumor size versus time, with a fitted line from our model. The Gompertzian growth equation attached here is the solution of the first-order nonlinear differential equation below, where Nt is the tumor size and N is the initial size. We let R, the random process in the growth rate, be the formal derivative of a Wiener process with mean mu t and variance sigma squared t. Said another way, RT is a white noise Gaussian random process with mean mu and variance sigma squared. Here is how we transform in the data. By using the monotonic transformation Yn, we have the double log function below. We transform the process Nt on 0 to k to Wiener process with a mean mu t with linear drift and variance sigma squared t. The transition probability density function is attached here, where N is the original tumor size and Yn is our transformed data value with mean value mu and variance parameter sigma squared. So if we know k, we can reduce the problem of estimation sigma and mu to a simple linear regression problem. Therefore, we define phi here. The new variable phi is normal and has mean mu times square root of difference of time and constant variance. K is determined by optimizing the R square of the regression. Here we have the quadratic regression plot of log R squared versus K. And with the regression function besides the plot, we can easily calculate the best k-value, which is 43.78. With the best k-value we got in previous slide, we can now calculate the likelihood number for different k-values. Here we choose k equals to 1.01, which is the first k we use for the plot. And obviously, the best k-value has a much better likelihood number than the other one. So that's all we got up to this point. And we also have other questions of interest. The first one is if early growth, say up to day 49, is used for parameter estimation, how well is the later growth predicted? Does the fit for 108 work well for 63? Only change the initial value in the model. The last one is the first passage time density to reach its tumor size can be computed for the noisy differential equation model and is compared to the data for each group of rat. Thank you so much.